Thank you to the organizers. I'm very pleased to be here, and it's a great and nice conference. We had several talks about the Hopfield model in the past few days, one by Sarah, one by Luca, this morning by Vincenzo. So there will be a little bit of repetition in the introduction. And I will present some recent mathematical results in the understanding of local minima of the Hopfield model. I will, oops, sorry. I will just very briefly recall, because we had already several introductions on the model, that the model can be viewed as an associative model in the field of biological physics, as a mean-field spin glass in the field of statistical mechanics, and as a single-layer recurrent neural network in artificial intelligence. And it is this last viewpoint who earned Hopfield and Hinton the Nobel Prize in Physics in 2024. So here are the, oops, sorry, I have to get used to this thing. So here is a definition for the model. So the system is of n spins. Okay, somewhere here, okay. The spin at site I, sigma I, can take two values, -1, and the state of the system is described by a configuration sigma of these n spins. I will denote by sigma n the set of all possible spin configurations, which is the n-dimensional discrete cube. Given an integer, big M, the objects we want to memorize are m particular spin configurations called the patterns and denoted by xi mu. So we can't hope to be able to construct a model that works for every possible choice of the M patterns, but rather for every typical choices of the pattern. And to do this, we will choose the patterns at random. What is considered typical is then determined by the choice of the probability distribution on the patterns. In this talk, I will assume that xi mu I is a doubly infinite sequence of independent and identically distributed random variables defined on a common probability space that have the same probability a half to be +1 or -1. And this was Hopfield's initial original choice. Using the patterns, we'll construct a family of overlap maps, one for each patterns. The overlap of the configuration sigma with the pattern xi mu is denoted by m and mu of sigma and defined, we saw the definition this morning, as the inner product of these two configurations normalized by n. So it measures how close sigma is to the pattern xi mu in the Hamming distance. And finally, we'll define an energy function, big E, which is a function on sigma n, as a function that depends on the patterns only through the overlaps. So given a smooth function f from R to R, E and M is defined as minus the sum from mu equals 1 to m of f of m and mu. Because the patterns are random, both the overlaps and the energy functions are random variables on this probability space. And you have noted that we have not defined just one model, but a whole family of models indexed by the integer, big M. And since we are interested in storing as many patterns as possible, we are interested in taking M as an increasing function of n. So, of course, different choices of the function f define different models. So we have a slightly different vocabulary with Vincenzo, Luca, and so on. So for me, the model is defined as a general half, was called in the 90s generalized Hopfield model. Okay, so my terminology is not the same as yours. So in the classical Hopfield model, F is a quadratic, oops, sorry. Oh la la. Yeah. F is a quadratic function. In the base-spin Hopfield model, which was recently renamed dense Hopfield model, F is x to the power p divided by p. And very recently, a modern Hopfield model was introduced in which f of x is exponential n beta x, where beta is a strictly positive parameter. So modern also refers to another model which was introduced by Ramsauer and co-author quite recently. This other model does not belong to the class of model I have just defined, so my results do not apply to it. And the terminology I have just been using is that of the paper of Ramsauer. Okay, so the meaning of, it's just that it has a lapse of time. So the meaning of the model in the context of a memory model is as follows. The energy function serves to store or learn the patterns in the sense that if the number of patterns is not too large, we expect to get the following sort of picture. So there should be very many local minima, and the global minima should be located at or very near the patterns and should be surrounded by very high barriers of energy. The functioning of the memory is described, as we learned this many times this week, by setting up a dynamics that typically a gradient dynamics that flips one spin at a time until a local minimum is reached. So if we start, for example, from this initial state, which is not too far from site 2, but very far from the other patterns, the dynamics will go downhill and eventually converge to site 2. So it reconstructs the memory site 2 from an initial partial information. And this is what is called an associative memory. However, if we had started from this other initial position, which is also close to site 2, we do not converge to it because we stay trapped in the first minimum we encounter on our way. So this means that local minima are important for the dynamics, but this is an idea that has been repeated several times since the beginning of this conference. So in his 1982 paper, Hopfield did some numerical simulation that revealed that if the number of patterns is small compared to the size of the system, a gradient dynamic started from an arbitrary state will end up at a pattern in 85% of the cases, in a state of no obvious meaning in 10% of the cases, or very near a pattern, but definitely not matching it. And this reflects the fact that I just said that when storing the patterns, local minima are created. Since they are fixed point for the dynamics, they act as memories and thus they are false or spurious memories because they were not intended in the system. Hopfield also found that there is a sharp critical threshold alpha C of about that 15, such that if M is larger than alpha Cn, then this picture completely breaks down. Whatever the initial distribution, the dynamics will never again found a pattern. And this gave rise to the notion of storage capacity, which is the largest number of patterns that can be stored in the system until some property of the memory is lost. As we heard yesterday in Luca's talk in 1985, Amit Gutwed and Sampolinsky initiated equilibrium statistical mechanics approach to the model, viewing the model as a spin glass model and using the replica method to obtain the free energy and predict the phase diagram. So by the end of the 90s, the predictions in what we could call the replica symmetric regime of regime of the retrieval phase was mathematically understood. So this is my joint work with Antoine Bouffier and the work of Talleyrand. But all this works indeed being concerned with global minima. We did not make much progress on the local minima because that was not the aim. Our aim was to be able to give conditions under which the global minima allow to identify the patterns. So in this talk, I'm interested in finding the local minima of the energy function, and so at zero temperature. So I will start by giving you a definition of our candidates for local minima. And so here, n is a finite integer independent of big N. Little m is a vector in the interval -1, 1 to the m of components mu. And f is a continuously differentiable function whose first derivative is strictly positive on the positive axis. I will call n mixed memory of type f, and I will denote by psi of m, configurations in the n-dimensional discrete cube that have the following form. for each I between 1 and n, the coordinate I of psi m is defined as the sign of the sum over the pattern, so from mu equals 1 to m, restricted to the indices mu such that mu is non-zero of psi mu I f prime of m mu. So this is a mixture of the patterns, and we will assume that the vector M has exactly little n non-zero components. So this mixture has exactly little n terms. So for simplicity, I will assume that the non-zero components are the first little n ones. And then we ask that the vector M satisfies the following system of equation. There are big M equations, one for each patterns, and it says that with P probability 1, the overlap of psi of M with psi mu converges as n diverges to M mu for each mu such that M mu is non-zero, and it converges to 0 otherwise. So let us check that patterns are mixed memories with little n equals 1. So if little n equals 1, I have only one non-zero component, m1. So this sum here reduces to just one term, psi 1i f prime of m1. Let's suppose that f prime of m1 is positive, then we get that psi of m is equal to psi 1. To determine m1, we use the first equation. The overlap of psi 1 with itself is obviously 1. And it is trivial to prove that the overlap of psi 1 with each of the other pattern goes to 0. So the initial patterns are mixed memories with just one term in the mixture. The way I derived this definition is by writing down the critical point of the free energy of the free energy functional of the Hopfield model, so the generalized Hopfield model, which I did with Antoine Bouvier a long time ago, and taking the zero limit, the zero temperature limit. So in 1985, in their very first paper on the Hopfield model, Amit Godfrey and Sampolinsky solved the system in the case of the classical Hopfield model with finitely many patterns. And they did it starting from temperature 1 and lowering the temperature to 0. They did the study partly analytically, but mostly through an extensive numerical study. And they discovered that mixed memories have well-defined deterministic rather than random mixtures. And they classified them into three groups: the symmetric mixtures, whose components are all equal, and the asymmetric one, whose components are not all equal. And they subdivided the asymmetric ones into the continuous and the discontinuous ones. And this has to do with the way that the solutions appear along the temperature when we lower the temperature. So they appear, not all of them, but some start appearing at temperature 1, and then the landscape evolves. And you have more and more and more of these critical points as the temperature goes to 0. So since I only studied the 0 temperature case in this paper, I can't really make this distinction. They also, their work also strongly suggests that the first two classes, the symmetric and continuous asymmetric solutions, should contain all the local minima of the energy function. And okay, so this is what is contained in the first paper. So I will be inspired by their results, and will look for solutions, mixed memory solutions of our equations that have mixture coefficients of the following form. So the vector little m has big M minus little n 0 components. The non-zero components come in blocks, little l blocks of identical components. So block 1 has size n1, and its components are denoted by m1, and so on. Block k has size nk, its components are denoted by mk, up to little l. In the next two slides, we are going to construct explicitly a family of such mixture coefficients. It is not complicated at all. It's just a few definitions, but it does take a few definitions. So if you don't follow them, it's not a problem. You can catch up on the talk afterwards. So here it goes. I will call L composition of the integer little n into little L Simons, or L composition of n. So this is a way of writing the integer n as the sum of a sequence of strictly positive integers, so n1 plus and so on, plus nl. Each of the nk's is positive, strictly positive. And here the order counts. Two sequences that differ in the order of their terms define different L compositions of n. I will say that an L composition is allowable if all its summands are even, so larger than or equal to 2, except the last one, which must be odd. And given an allowable L composition, we will construct a sequence of little l integers denoted by alpha nk and defined as 2 to the minus nk plus 1 times the binomial coefficient nk minus 1 chosen the integer part of nk minus 1 over 2. And I will then denote by gamma k the product of the first k alphas. So it is a product from s equals 1 to k of alpha and s. So here we see that changing the order of the ns defines different gammas. So this is why the order counts. So we have a sequence of little l gamma k's. I will denote by gamma n, little gamma n, the vector of components gamma k. And I will put in a set big gamma and O, the set of all possible vectors little gamma n that can be constructed from an allowable L composition of n for all L between 1 and n. So this is a construction of a sequence of numbers. And so far, it doesn't depend at all on the choice of a model. So now we will choose a model, which means we choose a function f. And I'll denote by gamma nf, the subset of gamma and O, whose vectors little gamma satisfy this system of inequalities. So we have L minus 1 inequalities, which state that 2 times f prime of gamma k must be strictly larger than the sum from s equals k plus 1 to L of ns f prime of gamma s. So this may look a bit difficult. In fact, it is very, very, very simple to check if a vector gamma n does or does not satisfy this, because everything is totally explicit. These are numbers we construct, and we give ourselves the function f. So this is not it is impressive, but it is not a difficult step in the construction. And we can now construct our desired set of mixture coefficients, given a vector little gamma in the set we have just constructed. I will denote by little m of gamma n, the vector of mixture coefficients whose last m minus n components are 0. And the non-zero components come into little l blocks of size nk and components given by gamma k.
Can I ask a clarification?
Yes.
The part before about the mixture didn't require any f.
No, it was a general.
What comes after? Is it all conditional upon the fact that you can define an energy? In other words, are you going to constrain your method to deal only with cases where those exchange interaction are symmetric? Or are you illustrating it for an energy, but your approach goes even beyond
I think we can cover a wider setting that I covered in the paper, but in the paper I defined the energy as a sum over mu of a function of the overlaps and mu. And
if there is no energy, like for example, if the things are asymmetric, there you will not have an Hamiltonian. Can you still do this?
Maybe we have to write things a little bit because I don't want to say something wrong. But I think the K you defined this morning can be treated. If this is, I believe, that's what I've been thinking during your talk.
Even if there's no F?
Yes.
Okay.
Yes.
It's even more general.
I think so, but...
Thank you.
Okay. And then I will call big M and F, the set that contains all the vector of mixture coefficients, so one for each little gamma and big gamma and F. I will add the vectors obtained by permutations of the components of these vectors. And I will also multiply all the coordinates by +1 or -1. And this is provided that F prime is odd, otherwise all the mixture coefficients must be positive. And here is what we can prove. For any odd integer n, if little m, the vector of mixture coefficients, belong to this set big M and F, then psi of M is an n-mixed memory of type F. So if we go back to Amit Gutford and Sampolinsky's classification, we can check that the set we have constructed contains all the odd and symmetric and continuous asymmetric mixture coefficients that they found numerically. And they don't contain any of the discontinuous asymmetric ones, for the reason that in that case, the solution does not belong to the hypercube simply. So it was tempting, since nobody ever found a solution that does not belong to that set, to conjecture that the converse of the theorem is true and that psi m is an n-mixed memory of type F if and only if little m, the vector of mixture coefficients, belong to the set I constructed. So of course, it would be nice to have more computer simulations, because clearly today's computing power has nothing to do with what it was 40 years ago. Yeah. And the next theorem proposition gives us the bounds on the number of mixed memories. So it tells us that this number is bounded by, behaves like m to the power n times quantity a and f that only depends on little n and on f, but not on the size of the system. So all the dependence on the size of the system is on the term m to the power n. So this tells us that when we store big M patterns in the system, we automatically create m to the power n mixed memories. So the next question is, are the mixed memories we constructed or minima? And the answer is yes, provided that m does not grow too fast. And how fast will depend on the choice of the function f. So I will consider the three functions that I have introduced at the beginning of the talk. So the classical Hopfield model, the p-spin Hopfield model, and the modern Hopfield model. And what we can prove is that under these conditions, each of the mixed memory we constructed is a local minimum of the energy function with p probability 1 and for all large enough n. In the case of the classical Hopfield model, m must be smaller than n over log n. In the p-spin Hopfield model, it must remain smaller than n to the p-1 over log n, so it's allowed to be much larger than in the classical case. And it's even more the case in the modern Hopfield model, where m is allowed to grow exponentially fast with n. Here, C beta, Cp, C2 are explicitly known, strictly positive quantities, independent of the size of the system. So if we specialize this theorem to the case little n equals 1, where the mixed memories are reduced to the patterns, these first two conditions yield the classical conditions for perfect retrieval. And in the modern Hopfield model, we get this bound here, which is very probably optimal because it's difficult to fit more local minima in a function on the hypercube. Okay, so I think I still have 5 minutes. Yes, okay. So I would like to give you the explicit mixture coefficients in the case of the Hopfield model and p-spin Hopfield model. So you will remember that the set gamma and F is constructed from the set gamma and O by selecting those vectors, little gamma n, that satisfy a certain system of inequalities. In the case of the classical Hopfield model, these vectors, little gamma, are constructed from allowable L composition of n, whose summands are all equal to 2, except the first one, n1, which must be, by definition, even, and the last one, nr, that can take only one of 3 values, 1, 3, 5. So the vector of mixture coefficients we get out of the form m of gamma n equals alpha N1, times a vector whose first N1 components are 1. Then we get L minus 2 pairs of identical components that decrease geometrically from 1 over 2 to 1 over 2 to the L minus 2. And the last component, or last 3 components, or last 5 components will depend on whether NL is 1, 3, or 5. So we have a very, very simple enumeration of all the local minima, depending on M, of course, of the classical Hopfield model. And so with this, it is easy to compute the energy function and have a look at how it behaves. So I will place myself in the simple setting well inside the retrieval phase. So I will assume that M over N goes to 0. Otherwise, I have to get into very complicated calculations. This was just for an illustration. Then we can prove that with P probability 1, for O mu between 1 and M, the energy of the patterns converges as N diverges to minus 1/2. So this is an old result. While the energy of the mixed memories converges to a number which itself is very close to 1 over pi, because you see it's exponential minus 1 over N1, 1 plus O of 1 over N1. So when N1 becomes larger and larger, this quantity becomes closer and closer to 1 over pi. And this tells us that as N diverges, the mixed memories concentrate on a sphere of radius square root 1 over pi in overlap space. And I added here a sentence that I would normally not add in a mathematics talk, but according to Amit Gutierrez and Polinsky, this is true also for the spin glass phase. So they say in a rather vague way that in fact these mixed memories as N1 diverges merge into the spin glass phase. So this is just one question that I'm very interested in for the future. So of course, we also see that the difference in energy between the global minima, which are at the pattern under this assumption of N, they are rather close to the energy of the local minima. We don't have such a big distance between 1/2 and 1 over pi. So this suggests, I mean, we can imagine that it is not absurd to think that the local minima will have an impact on the dynamics. So this picture is completely different in the p-spin Hopfield model, where now we can prove that for all p larger than 3, the set gamma and f is equal to the set gamma and O, so that the set of mixture coefficients is given by the set of all possible mixture coefficients we can construct. And this tells us that the set of mixed memories is common to all p-spin model with p larger than or equal to 3. And of course, this set contains a p equals 2 case. And again, it is not difficult to compute the energy in a simplifying case. So here, let's assume that m divided by n to the p over 2 goes to 0. This is again to be well inside the retrieval phase of the model. And what we can prove is that with p probability 1, again, for each mu, the energy of the mixed memory converges as n diverges to a quantity that now will decrease polynomially fast with n1. All the other n's are hidden here in this O term, and it decreases exponentially fast in p. So if we take p larger and larger, this quantity here decays to 0. And this corroborates the numerical findings of Hopfield and Krotov in their 2018 paper, who state that for large enough p, but they do numerical simulations, they run this memory, do the numerical simulation, and they state that for large enough p, the minima of the energy functions are free of spurious memories, such that each minimum is a semantically meaningful pattern, meaning the minima are now only the patterns. Of course, it is not literally true that the energy function is free of spurious memories. They are still there, but they become so shallow that what they see on the time scale they use, which I don't know what it is, that this local minima will not affect the behavior of the dynamics. And this is all I wanted to say.
questions?
Yeah. Is there any hope of classifying all the local minima? You mentioned this Hopfield, like 85, 10, 5.
Yes.
Is there any, maybe this is impossible, but is there any hope of like enumerating, since you're able to enumerate the mixed memories so precisely, is there any way of like maybe recovering these numbers?
So, two different ways to answer your question. The first is that I presented the local minima. In fact, I get all the critical points. To get the critical points that are not local minima, you really must work in overlap space because, as Gerard told us many times, I mean, it's difficult to make sense of a critical point that is not a local minimum. Yeah, okay. Joachim does not agree with this, but we can. I mean, I'm happy to look into it more. But I mean, the way I'm doing it is I go to overlap space. I can do that at 0 temperature. It's not a problem. And then I have all the critical points in the paper that I was presenting here, except that I didn't study the index and the properties because I wanted to put it in another paper. This one is too long. And the only thing you have to change is that now you look for solutions of your psi of m in a slightly different space, -1, 0, 1, because the sign function can take 3 values. And the definition of your allowable compositions, instead of having a not number as the last term of your sum, becomes an even number. And then you just do the same and you get all your critical points. Now, the other thing is classifying the critical points as beta varies. This is a difficult question. So as also Gerard mentioned on Monday, so you have to do some reverse engineering. It's the only thing I have in mind. I know that the limit points of all these points are those I constructed when the limit as beta goes to infinity. And then you use a fixed point argument and work backwards to your, but then the landscape, you know, at some point your points will disappear and so on. What is very difficult is this discontinuous critical points that, so I think we can classify all the symmetric and asymmetric continuous ones. But the discontinuous asymmetric ones, to me, they are a complete wonder. And that's really where I would like to have more numerical simulations. Because as you may guess, there's a lot of number theory in this paper. But these look like a complete miracle of number theories. I don't understand where they come from. I have absolutely no intuition. But the problem is that in their paper, and with Goodford and Sampolinsky, they say, we find a very few of them. And they give one example. And I was not even able to construct a second example. So this is to tell you that I have absolutely no intuition. But then if we had more examples, I guess we could build an intuition to find these points. But I'm not a numerical person. I'm totally unable to do that myself. So if somebody here is interested in doing it, I would be very much interested in it because this is the only thing that we are missing to get a complete classification of these points.
You mentioned that you were thinking about also potential generalization to dynamic cases.
Yes.
And I know you haven't done it yet, so it's an unfair question. But what would replace, even hypothetically, the minima in the dynamic case? Because the energy, crucial to what you showed here is the energy minima. But if I have a dynamic that is at
so what is crucial is the definition of the system of equation I'm solving. So blah, blah equals sine, blah, blah. If I have, and you have the same equation, okay? That's the only thing I care about, this equation. I'm solving this.
So this is like one spin flip stable configuration, something
Yes.
the dynamics.
Yeah.
So dynamics that has
non-conservative,
but it's like some synchronous or asynchronous
Yes.
dynamics, and these fixed points are just one spin flip stable.
Yes. So, I mean, we have to write it down, but actually, I'm only caring about this equation, not really about the energy. And this equation can be written differently. Perhaps we can change the J's for your case. I don't see...
Conceptually any road wrong.
No, but maybe there will be practical ones. So...
Yes.
So the question includes all the points of Amit.
All the points
that Amit from.
Yes, of course. This is why I made the conjecture that it was. There
is something that I didn't get for p bigger or equal than 3. So the conjecture is true for P equally P large, or is still a conjecture?
The conjecture that the converse of the theorem is true is a conjecture
For every P.
for every P. If I have a proof, I have it for all F. Otherwise, I don't have a proof. I mean, it will not be model dependent.
There is a last question. So I remember that in Human 88,
Yes.
in the last part, it was discussed.
Yes, so I was a little bit embarrassed about this because when I wrote the paper, so Chet Newman studied the Hopfield model, the Pace-Spin Hopfield model, the classical, he did all P's. And he also, so the question was to prove that for M equals alpha and alpha strictly positive, each of the patterns was located inside a ball such that on the surface, I mean, on the sphere, the energy on the sphere was everywhere higher than at the pattern. So this was a sort of a definition of a basin of attraction of the patterns. And inside in this paper, which I studied when I was very young, he also extends his proof to mixtures based on the definition of, based on the results of Hamid, Guthrod, and Zampolinski. And I initially thought that I would include it in my paper because I was certain his proof was correct. But then I realized he uses an hypothesis that he derived from Hamid, Guthrod, and Zampolinski's work, but this hypothesis is wrong. So one has to rewrite this proof. It's not difficult, but I couldn't put it in the paper because it was too long. So this type of result will be true. I don't see any difficulty, mathematical difficulty to do it, but there was a wrong assumption in the paper of Chet.
So for which mixed memories?
Huh?
For which definition of mixed memories? So
the definition I gave here,
yeah,
which is the correct one, Chet made an assumption that is not correct. That's it. And of course, it didn't have a very clear definition of the mixed memories. He had the definition of Hamid, Guthrod, and Zampolinski. So it was easy to make a mistake in the assumptions you could make on this. Okay, that's not a criticism at all. It's just that it turns out that he made the wrong assumption. And then the proof doesn't work because it contradicts my result. So in fact, what I say is that I'm not very interested in doing it because for me, it's too easy. Okay, so if somebody wants to learn these techniques, yeah. Yes, it's, I mean, for me, it is a student's problem. But indeed, I intended initially to include it in the paper because it was just natural. And I realized that I had to redo everything. But it's a different kind of techniques, different kind of, this is not much a probability paper. So in a sense, it was not possible to include it here.
Any more questions? Well, if not, let's thank Veronique again.